We're going to spend a lot of time drawing Lewis structures today. It's an important skill to master. The reason is it's the first step to determine if a compound is a polar compound or a nonpolar compound. The reason why this is important is if we know what kind of compound we have, then we know what intermolecular forces will hold it together in a solid. And if we know that, then we can draw its structure and predict or explain its properties, like having a high melting point or being able to dissolve in water. So here's the 5-step method. Let's use it to draw CH2O. My first step is to look at my atoms and place the least electronegative in the center. And you ignore hydrogen and fluorine when you do this. So I'm really comparing carbon and oxygen in this compound. Carbon is less electronegative than oxygen because it's further to the left in the table. So I put carbon in the center and I single bond all my other atoms to it. Now just try and space them out on your page. Step 2. I figure out how many valence electrons the atoms bring to the table. Carbon has 4, each hydrogen has 1, and the oxygen has 6. So that gives me 12 valence electrons to work with. This is how many electrons I'm allowed to have on my Lewis dot diagram. Step number 2 is to figure out how many total electrons it would take for each atom to become stable. Well, carbon needs 8 to become stable. Each hydrogen is stable with only 2 because it's in the first shell. And the oxygen needs 8 as well. So that gives me a total of 20. Next, I calculate how many bonding pairs are in my diagram. I do that by taking the total electrons and subtracting the valence electrons. This gives me how many electrons are shared in bonds. If I divide that number by 2, it tells me how many bonds I need on my diagram. Now if you look at the diagram, I've already placed 1, 2, 3 bonds. I need to put one more bond on there. My hydrogens are going to be stable with only one bond, but my carbon and my oxygen can share another pair of electrons. Final step, calculate how many lone pairs should be on your diagram. You do that by taking how many valence electrons you have minus how many shared electrons you have. That tells me how many unshared electrons are on my diagram. If I divide that number by 2, that tells me how many lone pairs I need. In order to place the lone pairs, what you do is you look at each atom and figure out if it's stable. If it's not, put a lone pair on it. So my 2 hydrogens are stable with 2. My carbon has 2, 4, 6, 8 electrons, but my oxygen only has 2, 4. It would take the other lone pairs in order to be stable. Compare this diagram to the one you did before we did our 5-step method. CH2O is an example of what I like to call a normal molecule, where you just have to follow the 5 steps with no little tweaks. But there are 3 other types of scenarios that you might come across. First is if your molecule has a charge on it. Following step number 1, I would put nitrogen in the middle because it's least electronegative, and I would single bond all my other atoms around it. Step number 2, determine the number of valence electrons. Nitrogen has 5, and each hydrogen brings 1 to the table. So that gives me 9. Now I do have to take care of this 1 plus charge. 1 plus means that my structure has lost an electron. So what I would do is subtract 1 electron from my valence in order to take that charge into account. If your molecule has a negative charge on it, you would add an extra valence electron in this step. Next, determine the total number of electrons. Well, nitrogen needs 8 to be stable, and each hydrogen needs 2. And because there's 4 of them, I need 8. So that gives me a total of 16. To calculate bonding pairs, I subtract those two numbers and then divide by 2 to give me 4 bonds. Now I've already placed 4 bonds on my diagram, so I don't need to add any more. Lone pairs, I take my valence electrons, subtract the number of electrons that are shared. That means I have no unshared electrons and I have no lone pairs. Now, to show that I have a positive charge on my structure, you put your diagram in square brackets and put the charge on the outside. The next scenario you'll come across is known as a resonance structure. When you're doing the method, it'll tell you that you'll need to place a double bond, but there may be more than one possible place to put it. What you do is you draw diagrams for all the possibilities separated by a double-headed arrow. SO2 is an example. So least electronegative would be sulfur because it's lower in the table than oxygen. Single bond everything else to it. To figure out how many valence electrons I have, each one of these has 6, so 6 times 3, that gives me 18 valence. Total electrons, sulfur and oxygen each want 8. I have 3 atoms, that gives me 24. For bonding pairs, subtract those two numbers and divide by 2. I need 3 bonds on my diagram. Now here is how we identify resonance. I could either place the double bond between that S and O and that S and O. So I draw both possibilities with a double-headed arrow in between them. Now for lone pairs. I take my valence minus my shared. That gives me how many unshared electrons I have. Divide that by 2. I need to put on 6 lone pairs. I look at each of the atoms and try and make them stable. This oxygen here has 2, 4, so it will need 2 lone pairs to get to 8. The sulfur has got 2, 4, 6 electrons, so it needs a lone pair. And this oxygen here only has 2 electrons, so it will need 3 lone pairs. And that gives me 1, 2, 3, 4, 5, 6 lone pairs. And I would use the same process on this diagram to place my lone pairs. And I get 6 as well. It was first thought that the double bond moved positions over time, flipping back and forth between the oxygens. And that's why we have this notation showing both possibilities with a double-headed arrow in between. But it was found that the distance between the atoms was actually exactly the same, and that's known as bond length, and that it was actually in between a SO single bond and an SO double bond. So we call it a bond and a half. So how this works, it means that the double bond electrons are delocalized. they're actually shared around the whole molecule. They're not directly attached between two atoms. The last scenario you'll come across is known as a molecule with an expanded valence shell. Here you'll see an atom that has more than 8 electrons on it and it's still stable. It breaks the octet rule. You identify these if you need more bonds to hold your molecule together than the 5-step method calculates. PCl5 is an example. Start by placing phosphorus in the center because it's least electronegative. And single bond 5 chlorines around the outside. For valence, each of my chlorines has 7 electrons, times 5 gives me 35. And phosphorus brings another 5 to the table to give me 40 valence. Total, I have 6 atoms, they each want 8 electrons, that gives me 48. For bonding pairs, if I subtract those two numbers and divide by 2, that gives me 4 bonds. But I've already placed 5 on my diagram. That's my clue that I have an expanded valence. At this point, I stop doing my method, and I add lone pairs to my diagram until I've placed all 40 valence electrons. Now, a common mistake people make is they forget that we've already placed 10 electrons in the bonds. What you do is you start adding lone pairs, making the outside atoms stable, and then add any extras that you have on the middle atom. Because each chlorine only has a single bond, it will need 3 lone pairs in order to be stable. This gives me a total of 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40 electrons. My diagram is complete. Notice that the phosphorus is breaking the octet rule. It is sharing 10 electrons. Let's say, for example, hypothetically, I had 42 electrons. My lone pairs around the chlorines would give me 40. In order to finish my diagram, I would put my extra lone pair on the phosphorus. Now this phosphorus is sharing 12 electrons. That's okay. You only want one atom to break the octet rule. So how is it possible for an atom with more than 8 electrons to be stable? Scientists aren't really sure. We just know, in nature, compounds like PCl5 exist. The best explanation I've come across is that atoms that have expanded valences usually have orbitals in the 3rd or 4th energy level, which means that they're larger. So maybe at this size, they can hold more electrons.